Hello students, in this session I would like to discuss some concepts of vector calculus. So this is the syllabus of BSc 4th semester Mathematics paper 2, Vector Calculus and Differential Equations, Karnataka University, Dharwad. So now see that basic concepts of differentiation of vectors, limits and continuity of a vector functions. So then after learning of this session, students would understand the basic concepts of differentiation, of how to differentiate the vectors, and also they should understand the limits and continuity of vector calculus. See that basic concepts of differentiation of vectors. First concept, a scalar function of a scalar variable. Let R be the set of all real numbers and set S be the subsets of real number R. If for every real number, for every variable or every number which belongs to a subset S, we associate a unique real number f of t, where t is a member of subsets, by some rule. Then this rule defines a scalar function of a scalar variable t. Hence, this f is a scalar function where f of t is a scalar quantity. Means what? This f is a scalar function that depends on the scalar quantity t there, where t is a member of S, then which we have that S is a member of R there. Then for example there, f of t equal to t square plus 5t. Means what? F is a function of t, so that everything it is a function of t, where t is a member of S, that S is a member of R. So that anyway this function is depends on this scalar quantity S. Next, vector function of the scalar variable there. Let R be the set of all real numbers and S be the subset of R. If for every t is member of subset S, we associate a unique vector f of t by some rule. Then this rule defines a vector function of a scalar variable t there. Thus, f is a scalar function where f of t is a vector quantity. So, but thing is that here t is a scalar variable, but f of t is a scalar function there. Understand? So then ultimately this f of t becomes a vector function there. So here f of t equal to f1 of t plus f1 of ti plus f2 of tj, f3 of t k cap is called vector function of a scalar variable, where f1 of t and f2 of t, f3 of t are all scalar functions of a scalar variable t, and also component of a vector, this vector function f of t, where I, j, k are unit vectors. These caps I cap, j cap, k cap are the unit vectors in the direction of x axis, y axis and z axis respectively. For example, R is a function, vector function, it is a f of t that equal to 2at square I plus 5tj plus 4t cube plus 1 k. This is the vector function of the scalar variable t there. Here, this is one example of a vector function of a scalar variable. teeth. And next we shall discuss that is scalar and vector functions. Vector point function. Scalar point function. If corresponding to each point of a region R, there corresponds a scalar denoted by that f of p. That p is any that points on that region R. Any points on region R. That means f of x comma y comma z. Then f is said to be a scalar point function for the region R there. For example, that f is a scalar point function, that is f of x comma y comma z, that equal to xyz plus y square z plus z square. There is no vector there. Vector. So each term which is the scalar quantity that. So that's why if you have any point in the region R, that corresponds to a scalar function, that is f of x comma y, that ultimately that f of x comma y comma z in terms of x y z there, x y z, then we shall see that is the vector point function. If corresponds to each point P of a region R, there corresponds a vector denoted by f of p or f of x comma y comma z, then that f is said to be a vector function for the region R. It means what? If you take any point in the region R that corresponds to a vector, then that f is said to be a vector point function of a region R there. For example, there. So this function which contains, that is the vector, each term has its own direction of, that is the x, y, z respectively. That see that f of x comma y comma z is x, y, z I cap plus y square z j cap plus z square k cap. These I cap, j cap, k cap are the directions of x axis, y axis and z axis respectively. That quantities, these are the quantities in the x axis, y axis and z axis respectively. And what do you mean by scalar field? The set of points of the region R together with the functional values f of p, that is vector point function, scalar point function f of p, is said to be a scalar field over the region R there. Means what? We have a set of points in the region R together with that scalar function, then which we called it as a scalar field over the region R there. For example, the temperature of any medium, which is what? Which is the scalar field. And next we shall see that is a vector field. That set of points of the region R together with the functional values, that means functional vector point function capital F of p, is said to be a vector field over the region R there. That means the set of points of a region R with that is a vector point function, then that which we called it as, that is the vector field over that region R. For example, velocity of a moving field at any instant of time, that which we have, that is means what? At any instant means which that velocity which contains, that is magnitude as well as the direction, means what? Which holds good for the vector point function definition, and which corresponds to, that is the any set of points of the region R there. That is what? That is which we called it as a vector field. Now let us see that some basic algebraic properties of that vector function. First, we'd like to discuss the definition of the vector function. A vector function f of t is said to tend to a limit L when t approaches to a limit infinity if for every epsilon greater than 0 there exists, however it may be small, there corresponds to a positive number delta which depends on epsilon, such that magnitude of that vector function minus L is less than epsilon whenever that is the distance between t and t naught is lies between 0 and that small positive number delta, then that is which we have said to be that is the limit there. And also in another way which can be denoted by limit of the vector function as limit t tends to that t naught is that is the L, that limit L. Next, algebra of limits, as we have learnt in every subject in the algebra. So we have to see that some properties of that. So suppose we have a vector functions f of t and capital F of t of a scalar variable t. Let g be a scalar function of a scalar variable t. Then limit of f of t plus capital F of t as limit t tends to t naught is the limit of that individual f of t as t tends to t naught plus limit of capital F of t as t tends to t naught. And same way which have been that see that here it is a subtraction, limit of the subtraction of two functions is equal to the limit of the subtraction of first function minus limit of the second function. And similarly, limit of product of two vector functions as limit t tends to t naught is limit of the first function into limit of the second function as t tends to t naught. And limit of magnitude of vector function is equal to the limit of the magnitude of the limit of the vector function. And last one, limit of the product of scalar function into vector function as t tends to t naught is the limit of scalar functions as t tends to t naught. And now we shall see that continuity of a vector function definition. A vector function f of t is said to be a vector is said to be continuous for t equal to t naught if the following conditions holds. This function exists at a t naught that. And second condition for this here, for every epsilon greater than 0, however it may be small, there corresponds to a positive number delta. It depends on always epsilon, such that magnitude of vector function f of t minus vector function f of t naught. This distance is very small whenever the distance of t and t naught is also less than delta. So that is what it is, the continuity definition, that continuity of a vector function. And also we have two properties of this continuity of a vector function. So one property here, the necessary and sufficient condition for a vector function f of t to be continuous at t equal to t naught is limit of a vector function at t equal to t naught is equal to limit of that equal to f of t naught. Another property here, if f of t equal to f of t1 I cap, f of t2 I cap, f of 3 of t k cap, then f of t is continuous if and only if f1 of t and f2 of t and f3 of t all are continuous, and each point of that vector function must be continuous. Then only we can have that is the f of t is continuous. Thank you. We have discussed here some scalar point function and vector point function and also definition of continuity limits of a function.